In this video, we'll be discussing variable valve timing. The schematics and information used in this video are typical of most vehicles. Always refer to the manufacturer's specifications before commencing any work. The purpose of variable valve timing, or VVT, is to allow the vehicle's engine to operate more efficiently through its power range, increasing low-speed torque and high-speed performance while decreasing harmful emissions. On some engines, VVT has eliminated the need for exhaust gas recirculation valves. This is achieved by varying valve overlap, which is not possible in an engine with a fixed position camshaft. The common types of VVT in production vehicles today include cam phasing, cam changing, multi-displacement, and active fuel management. In this video, we will look at cam phasing. These systems are generally actuated by the engine control unit. Cam phasing can also be described as continuously variable camshaft positioning. To achieve this, the camshafts are fitted with a movable cam gear called a phaser. This phaser is fitted to the intake camshaft. On some double overhead cam engines, they may be fitted to both the intake and exhaust cams. If fitted to only one camshaft, it's important to note that the phasing of the intake and exhaust valves are shifted in equal amounts. Overlap cannot be varied. On double overhead cam engines with phasers on each camshaft, individual angles of phasing can be achieved, and therefore valve overlap change is possible. This means, with a reduction in valve overlap, the engine will run smoother at idle with lower emissions. As engine speed increases, more valve overlap occurs, resulting in more power whilst maintaining acceptable emission levels. Remember, on engines fitted with cam phasing VVT, camshaft lift and valve duration are not altered. Only the valve timing is changed. The phaser allows camshaft to crankshaft timing to be changed while the engine is operating. Cam phasers can be either fully electronic or electro-hydraulic. Both need to be actuated by the engine control unit, or ECU. VVT will alter the volumetric efficiency of the engine. The phaser assembly has an outer housing that is driven by an engine timing chain or belt. Inside the assembly is a rotor with fixed vanes that is connected to the camshaft. Oil pressure that is applied to the fixed vanes will rotate the camshaft in relation to the crankshaft position. The assembly also contains a lock pin that prevents movement between the outer housing and the rotor vane assembly. The lock pin must be released by oil pressure before any movement takes place. Control of the valve timing is made by changes in oil delivery to either side of the vanes. Oil delivery to the cam phaser is controlled by a pulse width modulated, or PWM, spool valve. If the engine is operating at idle speed, then the ECU will not alter camshaft angle. This allows for a stable idle with minimal valve overlap. As the engine speed and load increases, the ECU will begin to change the valve timing by altering valve overlap. This keeps the engine speed stable under these conditions. The graphic shows angle of change only, not direction. Under high load conditions with minimal throttle plate angle, the intake camshaft is advanced. The objective is to open and close the intake valve earlier, therefore achieving higher engine torque at low engine speed. High engine speed combined with high load driving conditions requires substantial valve overlap. The ECU does this by advancing the intake and retarding the exhaust camshafts. This is the effect of increasing engine performance in this range. As the ECU monitors input signals, it makes continuous adjustments to the cam phase angle. This can be as much as 30 degrees advance or retard. On this engine, Camshaft position is detected using a Hall effect sensor. A 5-volt reference and a low reference is supplied from the ECU. A square wave signal is generated and goes to a monitored pull-up circuit. The cam phaser actuator is a pulse width modulated spool valve. As the ECM detects changes in engine speed, engine load, throttle position, coolant temperature, and intake air mass, it calculates ideal cam angle and controls ascent to the actuator solenoid valve by pulse width modulation. Some ECMs can use information sent from the oxygen sensors for final trimming of the phase angle. The actuator is a solenoid attached to a spool valve. When the engine is operating at idle speed, there is no demand for movement of the phaser assembly. Engine oil is delivered through the intake port to the spool valve. At this point, there is no control of the solenoid by the ECM, so the valve remains in the home or hold position. As the need for valve timing change arises, the ECM sends controls to the solenoid assembly. As the duty cycle of the control changes, the spool valve is moved. The higher the duty cycle, the further the valve moves. This is the apply position. Oil from the intake port is allowed to exit the spool valve and travel to the cam phaser. On the intake, this will cause the cam to advance, and on the exhaust, it will cause it to retard. Once the ECU has achieved the desired valve timing, the spool valve moves to the hold position and the timing angle is maintained. The higher the duty cycle, the faster the change in camshaft timing. This is due to the increased oil flow through the spool valve. The ECU houses a high side and a low side driver to perform the duty cycle control of the spool valve. Oil flowing from this passage into the phaser will cause movement in one direction. Oil moving from this passage will cause movement in the opposite direction. This allows us to have continuously variable and yet separate control over both camshafts. The ECU continually compares cam position to crankshaft position in order to monitor and detect any system malfunctions. Any fault detected will cause the phaser to default to its home position and a DTC will be logged. Scan tool data or an oscilloscope can be useful when diagnosing electrical and mechanical faults in a VVT system. Cam phaser systems that require oil pressure to operate require clean oil of the correct viscosity combined with regular servicing. Understanding the system before beginning repair makes diagnosis easier and more cost effective. Thanks for watching. Bye for now.